Hey everyone, in this video we're going to be talking about journal bearings and specifically looking at an example design problem. This video is part of a lecture series on mechanical design too. So below here we have an example problem of a typical problem that you'll be given as a design engineer or a typical problem you'll be given on an exam. So this problem is in two different parts. So we have part one and part three. There's another part in the middle that I took out, but just look at that, and then we have 5 questions in the first part and then 1 question in the last part. So it says a full journal bearing has a shaft journal with a diameter of 1.25 inches. The bushing bore has a diameter of 1.252 inches, and the bushing bore is 1.25 inches in length. So we immediately see that based on our content from the previous videos, we can clearly see that L over D is going to be equal to 1. The bearing load is told to be 620 pound force, and the journal rotates at 1120 revolutions per minute. Analyze the minimum clearance assembly and find the minimum film thickness, the coefficient of friction, and the total oil flow if the average viscosity is 8.5 microring. So the first part of this problem we can pretty much solve just by reading this part. So we don't need to read anything else. But we do have one more thing that is told to us in part D and E, and it's good to always read the whole problem before getting started, just in case there's more information that we're given later. So it says if the temperature is 100 degrees Fahrenheit, what oil SAE is most appropriate to fit with the above conditions? So we'll know that we have to worry with temperature eventually. And you're given the choice to change oil type or temperature to satisfy stable lubrication and minimize friction. State your new operating oil or temperature to satisfy the requirements. So let's go ahead and start this problem and really start with part A, B, and C first, which seem pretty straightforward and seem pretty similar to previous problems that we've done before. So first of all, I'm going to write some information down, and I'll go pretty fast through this problem just because of the fact that we already have some experience from the previous parts as to how to solve these problems. But obviously, you can slow down or check how I did it eventually, okay? So first things first, we know that W is equal to 620 pound force from the question. We also know that B, or the bushing diameter, is 1.252. D is equal to 1.25. L is equal to 1.25 as well, giving us an L over D of 1. Okay, that's going to be very important to us. And then our N value is equal to 1120 RPM, which turns out to be 18.67 RPS. And we're going to use a lot of RPS, so we want to convert that immediately if we can. Then next thing we can calculate C. C is equal to B minus D over 2. We're told we have to use the minimum clearance assembly, but there is no clearance given, so the minimum clearance assembly is just the assembly that we have in this case. So we have 0.001 is our clearance, which is in inches. Okay, and then from there we can find R over C, which is 0.625 over 0.001, which is going to yield a value of 625. And the reason why we're trying to find R over C and we're trying to find all this is in order to find our 3 different things, the minimum thickness, the coefficient of friction, and the total oil flow, is we're going to use the Ramon de Boyd charts, and we're going to use our Sommerfeld number in order to find it. So our Sommerfeld number, if you recall, is R over C squared times mu n over P. And based on this information, we can start plugging in for all of that. So we have that R over C squared is going to be equal to 625 squared. And then mu n over P, so mu is given to us as 8.5 microrain. So it's 8.5 times 10 to the minus 6 rain. So we can plug that in up there. We'll plug it in a second. Then P is equal to W over LD, which gives us a value of 620 over 1.25 times 1.25, which is 396.8 psi. And finally, we already have our N or our RPS, so we're good to go. So let me just plug in the value. So we have 625 squared times 8.5 times 10 to the minus 6 multiplied by 18.67, all divided by 396.8. And for S, we get a value of 0.156, okay? And another good thing here is you can actually see how long this is going to take me. If this were a full exam, you would probably have around 50 minutes to solve a problem like this, solve a two-part problem, or maybe an hour to solve this two-part problem. So you can see how long it's going to take within the video to see how long it could take you if you were going fast. And obviously, I'm not doing the math on a calculator, so it would slow me down a little bit. I already have the math solved, so that slows it down a little bit, but you can see how it would be pretty close to a realistic approximate of how long it would take someone who knows exactly what they're doing. So part A, we're told that we have to find the minimum film thickness. So for minimum film thickness, we're going to go to our chart of H0 over C. Then for our friction, okay, we're going to have R over C times F. And then finally, for our total flow, we have Q over RCNL. Okay, and we're going to go look for these values so that we can then find the three different values. So this is just looking up tables and being able to solve for those tables. So H0 over C is the first one we're going to look at. We're going to go to our formula sheet. So for H0 over C, it's here on the bottom left of the first page. So we're going to go ahead. I'm going to erase some of the previous annotations just so that we don't get confused. If it lets me, yep. Okay, so first things first, we have L over D of 1. We have a bearing characteristic number, or our Sommerfeld number, of 0.156. So our value of 0.156, this is 121416, so it's going to be somewhere in the middle here. And we're going to go up and find what our value for our H0 over C is going to be. So that's going to be 0.45 based on that. Then we can go find our RC over F. So again, we have 0.156, so somewhere around here. We're going to have the intersect with the line that is equal to 1, so it's going to be around here. And we can see that we have around 3.7 or 3.8, okay? It doesn't have to be precise, but as long as you get close enough, that should be fine. This is more to show how you're doing this rather than showing exactly the right value by interpolating or anything like that. So same thing here, 0.156, going to be somewhere around here. And we're going to go up to the line that's equal to 1. So we have this, and that gives us a value of around 4.23 or 4.25. So we're going to round up to 4.25. It's between the two lines. It's not exactly on 4.2, and it's a little bit closer to 4.2 than 4.3, but we'll keep it in the middle here. So we have those three values. So I can copy over those three values and then plug them in and solve for each different term. So we have 0.45, we have 3.7, and we have 4.25. And then if I rearrange this, I have H0 is going to be equal to 0.45 times 0.001, which is going to give me a value of 0.00045 inches. Then F is going to be equal to 3.7 divided by R over C, which is 625, which is going to give us a value of 0.000592. Remember, the coefficient of friction doesn't have units, so we're good to go. And then Q is going to be equal to 4.25 times R times 0.625 times 0.001 times 18.67 times 1.25. And so we get a value of 0.062 inches cubed per second. So we're done with part A, B, and C. Then part D, we're told that we have to find the oil So if the temperature is 100 degrees Fahrenheit, what oil is most appropriate to fit the conditions above? Okay, so what we're going to do is we're going to go to our oil chart. And we know that our viscosity is 8.5 microrain. So what we need to go look for is what temperature does 8.5 microrain work with on our graph, and what oil would work with microrain and temperature. So we're going to look, we know that we have 8.5 microrain, and we know that we have a temperature of 100 Fahrenheit. So based on that, we can find which oil we would use. Okay, so if we go to our oil chart, which is on the top left, we can write, so let me erase the annotations that we already have. So we can write that we have 100 degrees Fahrenheit, and we know that we have 8.5 microrain. So I'm going to zoom in a little bit here so that we can really find 8.5. So this is 6, 7, 8.5. So it's going to be this line right here, okay? And we're going to go across up to 100. So we have that this value would be right on the SAE 20 line. So that means that the SAE 20 would be most appropriate. Now, if you were between two lines, what I would suggest is that you go up a line. Okay, the most appropriate oil would be up a line because it would be more viscous. Okay, and more viscous means safer, it means there's more lubrication. So if you're ever between two lines, what you would do is you would go up if needed. Okay, in this case, you're right on the line, but if you were not right on the line, then you would go up. Okay, so that solves our part D to the problem. So going back, we can say that SAE 20 matches. So we would use SAE 20. Now, the next thing that's asked of us is part E. So let's read part E. Part E says you are given a choice to change the oil or temperature to satisfy stable lubrication and minimize friction. So the next thing we need to do is we need to figure out, do we satisfy stable lubrication? If we do, great, but we could minimize friction by lowering it. If we don't, we need to make a change. Okay, so in this case, we need to check stable lubrication. And in order to check stable lubrication, I'm going to write that mu n over P should be equal to or greater than 1.7 times 10 to the minus 6. But I'm going to make it equal to, so I'm going to use this equal to sign because I want to minimize friction. The lowest value of stable lubrication is going to give us the lowest friction because it means that our viscosity is going to be as low as we can. Okay, so that's going to minimize friction. Okay, so that's what it means in the question. So then we need to check what we have right now. So what we have right now is 8.5 times 10 to the minus 6 multiplied by 18.67 divided by 396.8. And we can see that if we have that, we get 0.4 times 10 to the minus 6, which does not satisfy. So we need to make a change, okay? And in order to make that change, there's different ways we can do it. We can either say, well, we need our mu to increase, or we need our speed to increase, or we need our pressure to decrease, okay? Now, if we look at our question, it tells us you're given the choice to change the oil type or the temperature. So we're only allowed to change the temperature or the oil type. So now we have to kind of decide based on mu, and that's it. Okay, we can't really change the n or the p. We're only allowed to change mu. So going back to our thing, we'll have to figure out what our mu should be based on stable lubrication. So what we can say is mu times 18.67, or we can put mu nu, okay, is multiplied by 18.67 over 396.8 should be equal to 1.7 times 10 to the minus 6 in order to satisfy stable lubrication. So we can rearrange the equation to find our mu nu. okay? And our mu nu is going to be equal to 36.1 times 10 to the minus 6 rain if we are to have stable lubrication. So now, from the chart, we can decide whether or not we want to change the temperature or whether or not we want to change the oil. So there's two different ways we can do this, and I'm going to show you both ways, even though you only have to choose one, okay? So if you go back to your chart, then let's erase this point. So we have the original point there, and what we need to have is we need to reach a value of 36 times 10 to the minus 6. So it's going to be a little bit above this point right here. So I'll put it in red, but it's a little bit above this point right here, 36.1, okay? And based on that 36.1, there's two different things we can do. We can either move and reduce the temperature and keep SAE 20, or we can change the oil and get an oil that would be at least the value that we need. So for the oil to be at least the value that we need a point right here, which would be SAE 50. And if we're going to the left, up, we need a temperature that's at least a value that we get right here. Okay, so the temperature here, if we go down, the temperature would be a little bit below 62 or 63. So we'll say that from the chart, we can say that we would need either a temperature is equal to 60 degrees Fahrenheit, or we need an oil that is SAE 50. Okay, so we could do either or. So now we're done with the first part of the problem. Okay, now we're completely done with this part. That's half of a 1 hour exam, let's say. So now let's look at the second problem that we're given. And what I'm going to do is I'm going to copy it over to the bottom so that we have it closer to the bottom. Okay. Okay, so we're told for the same journal bearing as above, you are to compare two different lubricants. Your assembly is still operating at 100 degrees Fahrenheit if you assume all lubricant losses are due to side flow. Determine the most cost-effective in dollars per second lubricant based on the individual costs below. So we have two different oils, and based on those two different oils, we're told that QS is loss of fluid. And what we need to figure out is which one is going to lose the most, or which one is going to be the most cost-effective option. So what we're going to do here is we're going to compare two different designs. So what I'm going to do is I usually like to split this into two parts, because it's going to be a problem where we're going to have to calculate stuff for SAE 40 and calculate stuff for SAE 70. And what we need to figure out is we need to figure out what our QS would be for SAE 40 and what our QS would be for SAE 70. Okay, which means that if we're looking for QS, that means we're also looking for Q first, because to find QS, we need to find Q, and that means we need to find Sommerfeld number, okay, for each one, okay, because they're going to be different. Now, based on the assembly that we have and at 100 degrees Fahrenheit, we're going to have different mu's, okay, so everything is going to be the same except for mu, okay, except for our viscosity. So our viscosity for SAE 40 and our viscosity for SAE 70 based on the temperature is going to be different. And then based on that, we're going to figure out which one has the highest loss. So going to our chart, if we go to our chart, we can go find out what our SAE 40 and what our SAE 70 values would be for viscosity. Okay, so I'm erasing all the previous information so that we don't get confused. So we have 100 degrees Fahrenheit is this line right here. So we're going to go and find what our value is for SAE 40, okay, and what our value is for SAE 70, okay. And we see that for SAE 70, we're around 75 times 10 to the minus 6, and for SAE 40, we're around 20 as our values. So 20 and 75. So I'm going to copy those over and write those over. So we're going to have a viscosity here of 20 times 10 to the minus 6 rane, or 20 microrane. And then here we're going to have 75 times 10 to the minus 6 rane. Now, based on this, what I can do is I can find my Sommerfeld number. My Sommerfeld number is going to be equal to 625 squared times 20 times 10 to the minus 6 times 18.67 from the previous problem, divided by 396.8. Okay, and then same thing here, I can find my S for this side. And so my S for 40 is going to be equal to 0.367. And my S for 70, I'll call it S70, is going to be equal to 1.378. Okay, so different S's based on the different viscosities. Okay, and I'm going to keep separating those two columns. So then from this S, what we can do is we can then find Q. So we can then go to Q and go find our Q for 40 and our Q for 70. So I can find my Q for 40 and my Q70. I can go find them in our Q chart. So I'm going to go do that really quick with 0.367 and 1.378. Okay, so we go back, we go to our Q chart, which is on the second page. Okay, and we have a value of 0.367, so that would be somewhere around here. Okay, and if we go look at that value, we're going to get, it's going to be a little bit more to the, around, it's going to be around here actually, a little bit more to the left. Okay, so 367 would be 0.3, would be around here, which would give us a value of 3.7 or 3.8 potentially. 3.8 is a good estimate for that, around 3.8. Okay, and then our 1.378 would be 1.2, 1.4, so it'd be very close to 1.4, a little bit before 1.4. And if we go look for that value, we get a value of 3.3. Okay, so this will give you a value of 3.3. So 3.8 and 3.3. So we can go copy those numbers over. So we have that it's equal to 3.3 and, sorry, 3.8 for SAE 40. And don't forget that that's not the value of Q, okay? We have to multiply by RC and L. We already have the values for RC and L, and this would be 3.3 times RC and L. And so that would give us a Q40 equal to 0.0564 cubic inches per second, and Q70 would be equal to 0.0481 cubic inches per second. Okay, now moving forward from that, I can then find my QS based on my Q. So I can find my QS from the chart. So if I go to my chart, I can find my QS over Q term. Okay, for 0.367 as well as 1.378, I believe. Yeah. So for 0.367, we have a value around here of, if I go up, I would get around 0.42 as my value. And then for 1.378, which is really close to 1.4, I would get a value of around 0.14, maybe 0.145, but we'll keep it as a 0.14 for now. So I would get QS is equal to 0.42. This is QS is equal to 0.14. Then I would multiply by Q, and I would get a value of QS is equal to 0.0233 inches cubed per second. and my right side would get a value of 0.0067 inches cubed. And then my last step, so my QS gives me how much I'm wasting per second. And my next thing I want to find is in dollars per second or in cost per second, how much I'm going to be losing. So I need to convert some information in order to get to whatever I would have for SAE 40 and for SAE 70 after. So in the question, we're given that 1 gallon is 231 cubic inches, and we know what a 55-gallon drum costs for each. We see that SAE 70 costs more, but we might save because we have less QS. We can see that we have less QS. So now it's about converting the information. So we just need to convert inches cubed per second into cost per second, essentially. So what we're going to do is the following. We're going to say cost per second is equal to 0.0233 cubic inches per second, okay? And I'm going to convert that. So I'm going to say there's 1 gallon per 231 cubic inches. So we get rid of the cubic inches here. And then I'm going to say that we have $400.99, okay, divided by 55 gallons. So that will give me my units will cancel, and I'll end up with dollars per second. And that would give me a value of 0.000735 dollars per second. If I do the same thing for SAE 70, the same exact procedure, for SAE 70, I can now compare and say that that would be equal, the cost per second would be equal to 0.000311 dollars per second. And so we can see that the clear winner, the clear economical solution is actually to use SAE 70. And that concludes this module, as well as this example problem and this part of the lecture. And it concludes module 4 completely to be able to be ready for an exam on module 3 and module 4.